Alright, this is part 4 of our lesson on graphing and analyzing rational functions. Alright, can rational functions have horizontal asymptotes and slant asymptotes? No. It's got to be one or the other. If you look at the rules, there's going to be a slant asymptote if the degree of the numerator is 1 greater than the denominator. But if the degree of the numerator is greater, then there is no horizontal asymptote. So these two things will never happen at the same time. Can rational functions have horizontal asymptotes and vertical asymptotes? Sure. We just saw that on the last problem. Vertical asymptotes and horizontal asymptotes. No big deal. Okay. Find all the asymptotes of this function. Alright, now just as far as your thought process, you should always try to factor this before you start talking about the asymptotes. Because what if the x plus 2 cancels out? Then there won't be a vertical asymptote. There'll be a hole instead. Now, you can pretty quickly tell that this is not going to factor because 5 is a prime number. So if you try to factor this, x squared is x times x. 5 can only be 5 and 1. Inner plus outer has to equal middle. There's no way that you can make a negative 2x out of this. So this is not factorable, but you should always check to see. So since nothing cancels out, I can go on with the process. The vertical asymptote is going to come from the denominator here. So that's going to give me a vertical asymptote of x equals negative 2. Okay. Now, as far as the horizontal asymptote, we look at the degree. The numerator is degree 2, the denominator is degree 1. So, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So, none. Now, it was important that we checked to make sure that this didn't cancel out, because if it did, there would be no slant asymptote either. But since the x plus 2 did not get canceled out, then we can look at the fact that the degree of the numerator is 1 greater than the denominator. So there will be a slant asymptote, and we will get it by doing long division. Now there's going to be a remainder, there has to be, but we will ignore it. So there will be a slant asymptote, but to find it, we will do the long division. So we will do x plus 2, and we will divide that into x squared minus 2x plus 5. Okay. Actually, you know what? I keep saying long division, but we could do synthetic if we wanted to. Anyway, I'll just stick with this. We could do, so x times x will make x squared. X times 2 will make 2x. We subtract by changing the signs, like this. Alright, so that cancels, but this makes negative 4x. And I start over. Oh, wait, and I bring down the 5 plus 5. Now I start over. X times negative 4 will give me negative 4x. These have to match. But then negative 4 times positive 2 is negative 8. Alright, I subtract by changing the signs. So those cancel out. But here I will get 13. Okay, so that's my remainder. I don't really need it. So the slant asymptote is just this part here at the top. Okay, this is the slant asymptote. So y equals x minus 4. Okay, so that is it for number 7. Number 8. What is the x-intercept and y-intercept of this function? So before I even look at it too hard, we will get the x-intercept by setting the numerator equal to 0. Numerator equals 0. We will get the y-intercept by letting x equals 0. In other words, plug in x. Okay, so setting the numerator equal to 0 for the x-intercept. Alright, so x minus 3 equals 0. Adding 3 to both sides, that gives us x equals 3. Alright. Oh, well, so it's x-intercept, so we really should say 3 comma 0. Alright, x-intercept's an ordered pair. Now, for the y-intercept, like I said, we're going to let x equal 0. So that means everywhere you see an x, that's going to become a 0. 0, 0. Excuse me. Alright, so that's going to leave, so I've got negative 3 over 1 times negative 2. Well, that 1's not doing anything. So that's just negative 3 over negative 2. Well, a negative divided by a negative is a positive. So that's just 3 over 2. So that's the y-intercept. So 3 over 2 is a y value. So that's 0 comma 3 over 2 is the y-intercept. Okie what dokie. Okay, that's it for number 8. Number 9. Does this have a hole? If so, blah blah blah. A hole happens when a factor in the denominator cancels out with a factor in the numerator. So if there's going to be a hole, we're going to have to factor to see it. So let's factor the numerator. Okay, so x squared is x times x. 10 is 2 times 5. If I want a negative 3 in the middle, I need a positive 2 and a negative 5 to make that happen. Meanwhile, this is the difference of two squares. So x plus 5 times x minus 5. Okay, so you see these factors that are about to cancel out. Alright, so the x minus 5 and the other x minus 5. So this is going to lead to a hole, alright, when things cancel out like this. Setting x minus 5 equal to 0, that tells us there's a hole at x equals 5. Okay, let's see. Oh, okay, so I'm like, what do we want in these blanks? So does it have a hole? Yes. Clearly there will be a hole. Now what will be the hole? Well, so far we know that the x value is 5. So there's going to be a hole at 5 comma something. We need the y value to go with it. Oh, nice of them to point that out to us. We want the y value that goes with it. How do we get the y value? We can use the function, but just the part that's left after you cancel out. Otherwise, you're going to get an error. Okay, so you could use a calculator for this, but you should be able to do it without a calculator. So we have x plus 2 over x plus 5. Alright, if you're lame, and use a calculator, it's going to look like this. X plus 2 over X plus 5. Okay, X plus 2 over X plus 5. Okay, and we want to know what the Y value is when X equals 5. So we will start at 5. Okay, so that's 7 over 10. 7/10. So 5 comma 7 over 10. That's the whole. Now what if you were not allowed to use a calculator somehow? Well, then you would just plug in 5. Substitute 5 for these x's. Alright? Which is probably quicker than using a calculator anyway. So if I did that, then this would become, it would be 5 plus 2 over 5 plus 5. Okay, so that's 7 over 10. Alright, that's easier than using a calculator anyway. So we should definitely do that. Alright, that's it for number 9. Alright, we're flying now, man. We're making good time. Let's see. Find the horizontal and vertical asymptotes of the rational function. Domain, range, increasing, decreasing intervals. Okay, well, clearly we have horizontal asymptote at y equals -2. Okay, y equals -2. Alright, that makes me worry. Did I put y equals on other horizontal asymptotes? I'm going to go check. Yeah, I did. Alright, so vertical asymptotes, we have 2 of those. So we have x equals -2 and x equals +2. Alright, x equals -2, x equals +2. Notice that horizontal lines are always y equals a number, vertical lines are always x equals. Alright, so do it right. Definitely don't just, if you just put -2 and without the y equals part, it's wrong. If you just put, oh, -2, +2, that's wrong. They're vertical lines. X equals -2, x equals +2. The domain. We'll have to do the 3 branches. The domain goes from -infinity to +infinity, but we have to skip over the -2 and the +2. Alright, so the domain will be written in 3 branches. So we will say from -infinity -infinity to -2, union -2 to +2, union +2 to infinity. Okay, so those are the 3 branches. Again, -infinity to -2, -2 to +2, and then +2 to infinity. Now for the range, we do y values from bottom to top. Now down here at the bottom, and we're doing both of these branches simultaneously, we will not do them separately. These 2 branches cover y values from -infinity up to -2. -infinity to -2. So that's our first branch of range. It's -infinity to -2. Now -2 there is an asymptote, so we will leave this round so as not to include it in the range. Now then there's a jump, there's a gap from -2 to 0. So then the function picks up, and we have y values again from 0 to infinity. Oh, by the way, the 0 is not an asymptote. The graph touches 0, no problem. It includes 0. So we will do a square bracket on the 0, 0 to infinity. Okay. Did they give us a spot for increasing and decreasing? Ah, it got cut off. What a shame. Let's see, can I make it jump up here? Alright, yeah, we'll squeeze it in. Alright, increasing and decreasing. I like to highlight for this part. So going from left to right, you always have to go from left to right when you do this. This part of the graph is decreasing. It's going downhill. And then it picks up from here. And once again, it is decreasing to right here. Okay, that's pretty ugly, but whatever. You know what, OCD. Okay, so like I said, it was decreasing from here to here. But then it starts increasing. So it's increasing from here to here. I'm messing it up again. I'm gonna leave it this time. And then picking up from over here, it's increasing again. It's going uphill the rest of the way. So I've got the green parts are increasing, okay, as you can see, and the pink parts are decreasing. I'll just make this pinkier so you can really see it. Okay, so we've got 2 decreasing and 2 increasing. Now when you do increasing and decreasing intervals, it's all about the x values. Okay, so over here, let's start from this. This x value, you can think of it as negative infinity. Alright, because it goes to the left forever. Now this x value right here is actually going to be negative 2 because it's approaching the asymptote right here, and x value of the asymptote is negative 2. This part over here, same type of thing. Again, this x value is negative 2. Alright, don't look at that arrow and think, oh, positive infinity. No, that's a y value. The x value is the asymptote, negative 2. Alright, same thing over here. Alright, this x value is positive 2 because the asymptote. Same thing down here. This x value is positive 2 because of the asymptote. And then over here on the end, alright, you can think of this as an x value of positive infinity because it goes to the right forever. Oh, right here in the middle, of course, this x value is 0. Almost forgot about that. Okay, so I guess we'll do the increasing intervals first. So the increasing intervals are the green ones. So we have one from 0 to 2 x values. So 0 to 2 union. And we have another increasing from 2 to infinity. Notice that increasing and decreasing intervals are always round parentheses. Alright, well, we have all these asymptotes which cannot ever be reached, but even the 0 is going to be round because it's decreasing up to 0, it's increasing after 0. Right at 0 is neither. Okay, so now let's do the decreasing interval. So we have a decreasing interval from negative infinity to negative 2. Union. And then we have another one from negative 2 to 0. Wait, you can see that. We have another one from negative 2 to 0. Okay, so that is it for number 10. Alright, and after that it goes to the last page with a couple more problems. So this video is long enough. So I'm going to go ahead and stop this video at number 10. Hopefully this lesson will only have one more video to it. I'll see you on the next video.